morning to all of you. I am Dr. Gaurav Saxena, Associate Professor in EC Department. So today I have discussed some terminology provided by the antenna, or we can say antenna basics. We have to be just given a brief idea which is associated with the antenna and wave propagation KEC 603. So what is the basics of the antenna? What is antenna? So basically, as per the definition of the IEEE, antenna is a transducer which converts electrical signal to the electromagnetic signal and electromagnetic signal to the electrical signal by if we use the antenna at the transmitting and the receiving end. So this is the basics of the antenna. So first of all, what is the how antenna radiates? So what is the radiation pattern of the antenna and what is the meaning of radiation pattern? So I discuss here. So basically, antenna, how antenna is to be radiated. So we can say this is a dipole antenna. Just I given a such example. So having a radiation resistance, this is the radiation resistance of that particular antenna. So what is the radiation resistance? Radiation resistance is a fictitious resistance which is connected to the series of the antenna, and we have to be consume that particular power that the antenna actually radiated. So that is called the radiation resistance. So by using the radiation resistance, how much antenna is to be radiated, we have to be calculated. So what are the other terms in terms of the what is the efficiency of the antenna, we have to be calculated by the radiation resistance and the loss resistance. So any antenna we have to be radiated some energy, and the some loss of the energy we have to be faded out. So the antenna efficiency is to be calculated. How we calculate the antenna efficiency? So how much power is to be radiated by that particular antenna? So that means the power radiated upon total power. How much power is to be incident? So this is the ratio of the radiation efficiency of any antenna. So if because the radiation resistance to be fed in the series of that particular antenna, so we can say a I current is to be flowing in that particular circuit. So the how much power is to be radiated? So we can say if the radiation resistance is RR, so we can say this is the I square RR is the radiated power, and what is the total power? So radiated power, and sum is the loss resistance I square RL. So RL is the loss resistance of the antenna, but in the case of lossless antenna, this RL should be 0. So we can say the antenna radiation efficiency is 100%. That means if we fed a 1 watt power, so all the power is to be radiated by that particular antenna. So we can say the antenna efficiency is 100%. So if we calculated by the radiation efficiency of the antenna, so we can say RR upon RR plus RL. So by simple, we have to be calculating the radiation resistance and the loss resistance. So we easily calculate the what is the antenna radiation efficiency. So if the antenna is to be good, if the radiation efficiency is to be high, for a practical antenna, we have to be assume that if we design an antenna for Bluetooth or any other application, so we remind that the antenna radiation efficiency is to be greater than the 50%. That means that at least 50% of power is to be, if we fed a 1 watt power, so at least 0.5 watt power is to be radiated by that particular antenna. And another terminology is what is the antenna radiation. So what is the directional antenna we have to be produces? What is the omnidirection, or we have to be use the isotropic antenna? So if we fed a isotropic antenna, so isotropic antenna is a fictitious antenna, or that means that this is not in the nature, or we can say because in the isotropic antenna the radiation pattern is uniform in all the direction. So this type of antenna is not to be made by any physical aspects. So this is the isotropic antenna having a gain is 0.0 dBi or 0 dB. So if we measure a voltage with comparison to the ground, or we can say if the voltage is 7 volts, so we can say this is higher than the earth voltage, or we can say 0 volt. So in this case, if we measure the gain of any antenna which is isotropic, omnidirectional, directional. So we calculate the gain with respect to the isotropic antenna having a gain is 0 dB. Or if any practical antenna, we have to be calculate the gain in terms of the dBi, or we can say dBi is the decibel with respect to the isotropic antenna. If I can say, so I design a Bluetooth antenna on the microstrip and having a gain is 6 dBi, so that means the this gain is to be higher than the 6 dB with respect to the isotropic antenna. So isotropic antenna is fictitious one, and the second one is omnidirectional. So this is a 3D. So in the case of R theta phi, that they giving a equal radiation in all the direction. But in the omnidirectional antenna, so azimuth angle is to be same. So in this case, if we design a omnidirectional antenna, so that means in the azimuth direction, but not considered a elevation direction. So azimuth direction, you have to just see that azimuth direction, the gain is constant. So we can say this is a omnidirectional antenna. And the directional antenna, you just see that this is the radiation pattern. What is the radiation pattern? This is the intensity of the power which have to be antennas to be radiated in a particular path. So we can say this is the radiation pattern of the antenna. We have to just see that this is directional in nature, or we can say in this direction is to be maximum and other direction is to be not appear. So we can say this is a directional antenna. By using the radiation pattern, you have to be see that this type of antenna we have to be designed. This one is isotropic, omnidirectional, and the directional one. This is the what is the antenna transition. So we can say this is the generator, this is the transmission line, and this is the taper transition. So electric field is to be generated, and this transmitter antenna which have to be transducer works as a transducer which converts electrical signal into the electromagnetic signal. And this is a receiver signal. So this is a guided TEM mode waveguide. We have to be produce it, and the receiver is here. So this electromagnetic plane wave is to be converted into the electrical signal. So this type of receiving antenna is called the receiver antenna, which have to be convert the electromagnetic wave into the electrical signal. So I already told you what is the radiation resistance. So this is the radiation resistance. So in that particular region, how much antennas to be radiated by using this radiation resistance. If the radiation resistance is to be high, that means that particular antenna is to be radiate more power, and the lost power is to be less. So what is the antenna region? So antenna has two types of region. This one is near field region or Fresnel region, or we can say far field region. So this is the antenna. So I choose a dipole antenna having a length is lambda by 2. So we can say this is a half wave dipole antenna because the length is lambda by 2. Lambda is the proportional to the wavelength. So we can say half wavelength antenna we have to produce it. And this is the length of that particular antenna, or we can say this is the D. In case of half wave dipole antenna, this is lambda by 2, and you have to see the lambda by 4 antenna, lambda antenna, or we can say any other antenna. So the radiation distance R1, you have to see that this is the radiation resistance R1 and this is the radiation distance R2. So how we calculate the what is the reactive region, near field region, and what is the radiating near field region, or we can say what is the far field region or Fraunhofer region. So if your antenna is to be calculated in the near field region, or we can say if I design an antenna for near field application, so we can say that particular antenna is to be used at the near field region, or we can say if your antenna is to be designed for far field region, so we can say this is far field region, or we can say how we can utilize that your distance is to be near field or far field. If this R1 distance is to be 0.62 or under root d cube by lambda, which is less than this, so we can say this your antenna is to be reactive near field region. So in that particular region, no communication occurs because that particular electric field is to be reflected back to the antenna. But in the radiating near field region, or we can say Fresnel region, which one is, if your distance, this r distance or d distance is less than 2d square by lambda, where d is the length of that particular antenna and lambda is the particular wavelength which have to be desired that particular frequency by that particular antenna. If your distance is to be measured, r2 distance is to be measured, which one is less than 2d square by lambda and greater than 0.62 under root dq by lambda. So we can say that particular region is to be the radiating near field region, or we can say Fresnel region. So this type of region is called the Fresnel region, or many application in Fresnel region we have to be performed here. And the far field region, which one is Fraunhofer region, if your distance is d is, or we can say r2 distance or d distance, which one is greater than 2d square by lambda. So we can say your practical application, that particular antenna is to be Fraunhofer region or far field region. So this is the comparison between the what is the wave propagation difference in near field non-radiative reactive region, radiative Fresnel region, and far field Fraunhofer region. So we can say this is the antenna. If you're in the non-reactive region, so this one is this, if this distance is 0.62 under root d cube by lambda. So we can see that if we this wavefront is to be here and some reflection is to be back here, so no power is to be targeted or radiated in that particular region. So most of the power is to be reflected back that particular antenna. So this is not used in that particular any applications, but the radiative Fresnel region is to be used. So in that case, if your antenna distance, which one is less than 2d square by lambda and greater than 0.62 d cube by lambda under root d cube by lambda, so this radiative region is here occurs. In that particular case, many of the applications to be used in near field radiative region. So in local area network, if we connected in home automation system, by using the home automation system, we have to be use the radiative Fresnel region. In that particular case, the antenna height or that particular connectivity we have to be measured, which is less than under 2d square by lambda and greater than the 0.63 under dq by lambda, where lambda is the frequency which has to be transmitted that particular antenna. And the far field region, we have to see that for long distance communication we have to be use the far field region, or we can say you see that the wavefront is to be forwarded and no one is to be reflected back by that particular region, or we can say for long distance communication we use the far field region, or that in that particular case the antenna height or what is the distance we have to be measured by that particular antenna, which one is greater than 2d square by lambda. So in that particular region, the r distance is to be greater than 2d square by lambda. For that such application, we can see that we can use that, or we can say that that particular antenna used as a far field region. And this one is the what is radiation pattern. So radiation pattern is to be defined by here. The radiation pattern, on the other hand, we have to be see that the what is the power of that particular function in the spherical coordinate system. So we can see that, so this radiation pattern is to be in the r theta phi in the spherical coordinate system, or we can say this is the main lobe and this is the side lobe. So side lobe intensity is very much less with respect to the main lobe intensity. So we can say this radiation pattern is to be of an antenna which is directive in nature. So that means directive in nature, that means in a particular direction that antenna radiation pattern is high, and other direction we can see that the back lobe see that the radiation intensity very poor. So this is the side lobe. So this is unwanted signal we have to be propagated by that particular antenna in other directions. So how we calculate the half power beamwidth of the antenna, and what is the half power beamwidth? So if I design any directive antenna, so the radiation pattern or E feed of power pattern is to be designed in that particular fashion. So this is 0 dB, or this is how much 3 dB down here. So we can say this is the 3 dB down. This is minus 3 dB down. So this angle between them, this is the half power beamwidth. And how we calculate the beamwidth of first null, or we can say BWFN. So in isotropic radiator, or in that particular fashion, so that means the half beamwidth of first null is half of half power beamwidth. So that means how much, this is the first null, we have to be appear. So how much, this is the angle between the two nulls, that is called the beamwidth of first null. So we have to be see that this is the any radiation pattern of any antenna, or we can say that the half power beamwidth of that particular antenna is 40 degree, and the beamwidth of first null beamwidth, which were same, which one is 74 degree. So this is the r theta phi plot, and this is the xy plot. So we easily calculate the what is the half power beamwidth and beamwidth of first null between the antenna radiation patterns. So what is the beamwidth? Beamwidth is the angular separation between the two identical points on opposite side of the pattern maximum. So which is already we have to be watch out in that particular this antenna radiation pattern. So we can see that this is the main maximum, and what is the 3 dB down? 3 dB down is 0.707 of maximum amplitude. So this type of we have to be plotted. So this is the half power beamwidth and beamwidth of first null, or we can say this is the beamwidth of first null. Beamwidth of first null of that particular, that means the angle between the two first null radiation patterns. So the angle of that particular two radiation pattern of first null, that is called the first null beamwidth, or beamwidth of first null. So what is the normalized field pattern? So if the electric field intensity in a theta comma phi direction, which are same in r direction, so we can say this electric field is to be function of theta comma phi, or we can say theta or phi is to be varied. So the electric field intensity is to be varied. So what is the E theta comma phi in any direction, and what is the maximum E theta comma phi if we divide it? So this is the normalized field pattern. So normalized field pattern and the normalized power pattern are same if we divided the maximum power intensity to that particular intensity. So we achieve a normalized power pattern. So first example, we have to be calculated how we calculate the half power beamwidth. So antenna having a radiation pattern is E theta is equal to cos square theta, for theta lies from 0 to 90 to find the half power beamwidth. So we have to be calculated at the half power beamwidth, that means this is a electric field pattern. So we can say this one is 0.707, or we can say 0.707 is equal to cos square theta. So we easily calculate what is cos theta. Cos theta is equal to under root 0.707, because this radiation pattern E theta is to be here by using the, so we can say 3 dB down, that means that this is 0.707. So we put cos square theta is equal to so cos theta is equal to under root 0.707, and then theta is equal to 33 degree. So this theta is 33, this is half theta. So we can say we calculate this theta is equal to 33 degree. So total half power beamwidth is calculated by half power beamwidth, which one is 2 theta, or we can say 2 into 33 degree, or we can say 66 degree. So we easily calculated if the electric field pattern of in terms of theta and phi is to be given. So we easily calculate the half power beamwidth. So and if we calculate what is the BWFN, or bandwidth of first null beamwidth, So this one is greater than, this is twice of, just equal to twice of that, or we can say which one is 132 degree. So which is approximate 132 degree in the case of this. So we easily calculate the half power beam width and the beam width of first one. So next question is, what is beam area? How we calculate the beam area and what is the meaning of beam area in terms of the antenna? The beam area or beam solid angle of the antenna is given by the integral of the normalized power pattern over a sphere. So that means the what is the normalized power pattern? P and theta comma phi sin theta d phi. If phi lies from 0 to 2 pi, which is azimuth angle. So in this case, the phi limit is 0 to 2 pi, and this is the elevation angle. So this elevation angle theta lies from 0 to pi. If we calculate the normalized power pattern in that particular region, so we achieve a beam area or beam solid angle. So beam area, beam solid angle, the unit is steradian. But 1 steradian, we know that if we convert 1 steradian into the degree, so we provide a 180 upon pi ka whole square, degree square, degree square. So that means 1 steradian is equal to 3282.3 degree square. So degree square is this one is, so this provided degree square. So beam area also to be calculated by in terms of the half power beam widths in theta and phi angle. So how we calculate is beam area? Beam area is to be calculated by theta HP into phi HP. So we calculate the theta HP half power beam width and phi HP in the region of azimuth angle and elevation angle. We have to be calculate the half power beam width, then we calculate the beam area omega A in terms of theta HP and phi HP. What is radiation intensity? Power radiated. What is the radiation intensity of an antenna? If I can say radiation intensity of that antenna is this, and this. So what is the meaning of radiation intensity of the antenna? So what is the power we have to be of antenna per unit solid angle they have to be radiated? That is called the power radiated of an antenna per unit solid angle. That is called the radiation intensity. So if any antenna which has to be radiated some power, so per unit solid angle how much power is to be radiated, that is called the radiation intensity. And radiation intensity is to be calculated by R square into W radiation in power. So power density we have to be calculated, and we have to be calculated by radiation intensity by using this formula. And what is the beam efficiency? So we can say any radiation pattern, if we draw a radiation pattern of any antenna, direction antenna, so some major lobes and minor lobes we have to be appear. So what is the major beam area? So total beam area, which is the sum of major beam area plus minor beam area. So beam efficiency is to be calculated by, this is the omega total. So total beam area is to be sum of the major beam area plus minor beam area. So this is major lobe, this is minor lobe. So beam efficiency is to be calculated by major beam area upon total beam area. Total beam area is major plus minor beam area. So if we calculate the minor beam area upon total beam area, which is calculated by the so we can say this factor is to be stray factor, and the major upon total, which has to be calculated by beam efficiency. So beam efficiency is the ratio of major beam area upon total beam area. So total beam area is to be divided by major beam area plus minor beam area. So and the stray efficiency, stray factor we have to be calculated by the minor beam area upon total beam area. So minor beam area upon total beam area, So stray factor plus beam efficiency, the sum of this is 1. So this is a dimension less quantity, and we have to be radiation efficiency, which we calculated in the 0.2, 0.5, 0.8. So beam efficiency is higher than that. That means the major beam areas to be high. So what is directivity? Directivity of antenna is to be calculated by the power density, yani maximum power density of that particular radiation intensity of that particular antenna or test antenna upon average power density. So maximum power density upon average power density per unit area, that is called the directivity. Our directivity is to be calculated by how we calculate the average power density. Average power density will to be calculated by 1 upon 4 pi p theta comma phi d omega. So how we calculate the directivity? Directivity is to be calculated by 4 pi upon omega A. Omega A is the beam area. Total beam area is to be calculated. If we calculate the total beam area, so we easily calculate the directivity of that particular antenna by using the formula upon 4 pi upon omega A. And omega A, how we calculate the omega A? This is the normalized power pattern, p and theta comma phi sin theta d theta d phi, where theta and phi lies from 0 to 2 pi and theta lies from 0 to pi. By using these, we have to calculate the beam area, total beam area, and 4 pi upon total beam area, which reflects the directivity, and the unit of directivity is dB. Suppose a antenna only which having a beam area is 2 pi steradian. So what is the directivity? So we easily calculate the formula. What is the directivity? Directivity is the ratio of 4 pi upon omega A. Omega is the beam area of that particular antenna. If the beam area of that particular antenna is 2 pi steradian, so we put 4 pi upon 2 pi, that is 2, or we can say 3.01 dBi. So we convert this directivity to dBi. So by using the 10 log 2, how we calculate the directivity d in linear form, how we convert into the dBi. So 10 log base 10 into 2. So 2 is the directivity in linear form. If we convert in dB, so 10 log base 10, and this is 2 log 2 base 10, which one is 0.3010, and we multiply by 10, so we can say 3.010 dBi. So that means this directivity is 3.01 dBi. That means this directivity is enhanced with respect to the isotropic antenna by 3.01 dB. Or for short dipole, the area is 2.67 pi steradian. So directivity of short dipole is 1.76 dBi, and for isotropic antenna, directivity is 1, or we can say the directivity of isotropic antenna should be 0 dBi, because log 1 is 0. What is gain? Gain is the ratio of maximum radiation intensity of the test antenna upon maximum radiation intensity of the isotropic antenna. This is the ratio of that particular this. And how we calculate the gain? Gain we have to be calculated by this formula, 41253 square degree upon theta hp into phi hp, or we can say what is the antenna under test, what is the maximum radiation intensity of the test antenna upon maximum radiation intensity of the reference antenna, or with respect to the if we use a reference antenna as a isotropic antenna, so this is isotropic antenna in this particular case in the reference antenna, and what is the gain of that particular reference antenna, we have to be multiplied by them, so we easily calculate the gain. So one more question we have to be calculated, what is the relation between gain and directivity? So gain is the efficiency, radiation efficiency into directivity. So gain is always less than directivity because if I can say some important question we have to be asked by university exam, if the gain of that particular antenna is 10 dB and the radiation efficiency is 90%, so what is the directivity of that particular antenna? So in that particular case, so you see that this gain is given in dB and radiation efficiency is given in linear form, and they asked you the question what is the directivity in linear or dB form. So first we have to be convert this gain into the dB to the linear form. So 10 dB, which one is equal to the 10 log base 10. So this is a power pattern. So we can say 10 dB, which one is equal to the 10 log G in linear form. So what is the G in linear form? So we have to be choose that. So what is the anti-log of this? This one is 10. So by default, the gain of 10 dB in linear and dB form, which are same, which one is 10. Then we apply this formula, how gain is equal to efficiency in directivity. So this is the 90%, or we can say this is 0.9. So gain is 10 and this one is 0.9. So what is the directivity? So directivity is 10 upon 0.9. So this one is 11.11. So the directivity of that particular antenna is 11.11, or we can say if we choose this directivity in decibel form, so how we calculate the directivity in decibel form, which one is 10 log base 10, 11.11. So we easily calculated by in directivity in decibel form. This is important question which is have to be asked in university exam. So I just remind that what is the relation between the gain and the efficiency and the directivity. So you solve this question by using this method. So this one is what is antenna aperture. So how much antenna is to be received that particular power? If I can say is some antenna which has to be radiated some power and receiving antenna is to be receive that particular power. So if I radiate 100 watt power in the air, so what powers that particular antenna is to be received? So by using the aperture area, we have to be decided that what is the effective power is to be received by that particular antenna. So this is the ratio of E square upon Z, where Z is the impedance of air, which one is 377 ohm, or E is the what is the electric field or voltage which have to be appear at the receiving antenna. So E square upon Z is the ratio of that particular. So we can say this is the aperture, this is the power, how much power is to be here, and how much aperture angle we have to be received. So what is the actual power we have to be received by that particular antenna, which is decided by the aperture area. The unit of aperture area is meter square. So this is the aperture area of that particular horn antenna. So how much power? So power is to be radiated in that particular fashion. So how much power is to be received by that particular antenna? So if the greater the aperture, so greater the receiving power of that particular antenna, or we can say gain of that particular antenna also increases. So what is the aperture efficiency? So effective aperture area upon physical aperture area, there is a ratio of effective aperture area to the physical aperture area, that is called the aperture efficiency. So in this case, effective aperture area always less than physical aperture area. So this is the some example. So directivity in terms of the aperture area, which one is 4 pi AE upon lambda square. So another important terminology with respect to the antenna is effective height. So this effective height topic we have to be covered in next lecture. Thank you.